Okay, in the prior chapter you learned how to create your first multiple linear regression, your first predictive model, and an experiment here. Now we need to take on the task of selecting variables. So initially, we simply selected everything that was available. However, that's often not what we want to do. We need to balance the need for accurate, good predictions against the threat of overfitting. So overfitting happens when we have a prediction that's too custom fit to the data that we have. I talked about this briefly in the prior chapter. So the problem is that when we have a data set, like we have right here, there's a chance this data set is not a perfect random representation of the population we're actually interested in. Even with big companies, Amazon is doing 1 million transactions every couple of hours or so. There's still a chance that the people who start shopping at Amazon next or in the future aren't going to be exactly represented by the prior people who've shopped at Amazon. Maybe they've targeted some new market or something like that. Yeah, they're going to be very similar, but over time, things change. So the idea is that if we come up with a really accurate custom fit prediction to this data set, it may not translate well. So what we want to do is often scale back. There's lots of different things we do to prevent overfitting. You learned in the prior chapter about how we split data into a training and a testing set to avoid overfitting or minimize it. We can also reduce the number of variables that we use in our prediction. In particular, we can eliminate some of the variables that have very small or minor effects. That maybe one of the variables we use really truthfully doesn't have an effect on whether or not someone purchases a bike. But in the sample we collected of 1,000 records, it just happened to be that with those 1,000, it did have an effect. Well, what we want to do is remove those variables that don't have a very large effect from future predictions. And we're not totally solving the overfitting problem. It's just further minimizing the likelihood that we're going to overfit. So we're going to learn 3 techniques in this chapter, starting with filter-based feature selection. Now, they each have various advantages and disadvantages, and there's not one that's always the best. So grab this pill. This has 1 input, 2 outputs, and here's what we want to do. Let's grab all of these and let's put it in between the select columns and the split data. So we want this sometime before the data gets split, but we also may want to, there may be certain fields we know we'll never want that we want to eliminate with a select columns like this. Now, as a reminder, I have edit metadata here because I'm pulling from a database, and I have to cast all of my numeric variables into numbers so it knows that they're not text. If you're using the original CSV file, it's a non-issue, so you just have bikebuyers.csv. Anyway, so filter-based feature selection has 2 outputs. This says filtered dataset, and this one says features. All right, what we want is the filtered dataset, but I'm going to show you what happens with both. So here's how this pill works. Super useful in certain contexts. What it does is it says choose a scoring method, first of all, and now you've learned already the Pearson correlation, but each of these scoring methods are techniques for analyzing the relationship between 2 variables. They're bivariate statistics. They tell us how much one variable changes as another variable changes. So remember, that has some advantages and disadvantages. The advantages, that's what we're interested in. We want to know how correlated each of our potential independent variables is with the dependent variable. So that tells us we're going to need to mark what the dependent variable is. Remember, we did that down in train model, but we're up here. It doesn't know yet that purchase byte numeric is our dependent variable. So first things first, let's grab that purchase byte numeric and let it know. And it even gives us a clue here. Select a single column. So we know that means the dependent or target variable. All right, with that selected, it then what it's going to do is it's going to look at every other variable and calculate the Pearson correlation with purchase byte numeric. So you may remember the correlation matrix we made in Excel. It's essentially doing that, but with just the dependent variable. It's not looking at all the inner correlations among the independent variables. However, here's what the last thing it wants to know. Desired number of features. So it's going to go through and calculate a correlation of each independent variable with purchase byte numeric. It's going to rank order sort them. And then all we have to do is tell it that we want to keep the top n, or how many features do we want to keep. And it's going to keep the ones with the highest correlations. So let's say we want to pick 6 of them. I think there's 9. Oh, I don't even remember it now. How many do we have? 12 columns. So that means after taking out purchase bike, there's 11 independent variables. So by choosing 6 right here, it's going to automatically drop the 5 with the smallest Pearson correlation. Now, there's a clear advantage and disadvantage of this technique. The disadvantage, hopefully you've already thought through this. The disadvantage is the same reason why we don't rely on correlations and why we've shifted to multiple linear regression in the first place. Is because a correlation does not take into account the intercorrelation of each variable with all the other independent variables. So it could be that among these variables that it analyzes, that it comes up and says, okay, income has a really big effect on purchase bike numeric, but it doesn't take into account the fact that children, cars, age, and education overlap with income quite a bit, which means then that income only has a small effect left over after accounting for the effect of all those other variables. So this tool doesn't take that into consideration, this filter-based feature selection. However, what's great about this tool is that it appears up here in the process before you get to the trained model. What that means is I can pull in the entire data set, trim it down to the 12 or 11 that I think are most likely to have an effect, and then dynamically choose the 6 best ones. Now, that is a pretty important advantage in certain contexts. Think of situations where you may get a lot of variables and the importance of each variable changes over time. Or perhaps I don't have enough seed data to begin with that I trust the trained model that it's going to come up with. I only have 1,000 records or maybe just 100 records, but I want to get something started and I trust that down the road, the variables that are truly most important are going to shift a little bit. Either because I don't have enough data or B, because I expect different customers to start shopping at my store. And the things that are important that explain what they purchase may change over time. Well, the great thing is filter-based feature selection will automatically adjust. And every time I rerun this model or retrain it, it'll dynamically pick the top 6, and then those 6 could change. I still send in all the original data, but the best ones change. So what other specific context is this useful in? When we get to text analytics, hopefully if you get that far in the class or in the book, you'll see that we'll often take text and hash it up into hundreds, even thousands of words and phrases. And we want to test all of them and see which words and phrases have the biggest effect on some outcome. This is a great tool because with thousands of different options, you can say only pick the top 10 or 20 or however many you want words and phrases that impact some outcome. So of our options, this is probably the least accurate, but most dynamic or useful in an automated machine learning environment. So anyway, let's run this whole thing and see what we get here. Okay, this is all done. Let's see here. I'm going to first, let's go to the output 2 features. And this will show you, I wish it was vertical instead of horizontal, but it shows you the correlation of each variable with purchase bike numeric. Purchase bike is a 1 because obviously correlation with yourself itself is a 1. But then it's rank order sorted the rest of them. Cars has the next highest correlation. Children, marital status, age, then income, gender, education, occupation, community, region do almost nothing. It just rounded them to 0. However, though, I shouldn't say that it rounded them to 0. They're exactly 0. Why are these 4 0? Because if you remember when we learned how to do our MLR before, I think it was it region? No, education. It was one of these categorical variables that actually had the biggest effect. So how could they be 0 now and have 0 correlation? Well, think back to when we learned about Pearson correlation. It's something we use between 2 numeric variables. These are all categorical variables. You can't calculate a Pearson correlation between a numeric, like purchase bike numeric, and a categorical variable. Therefore, they're all 0. So we're not really getting a good understanding or a good filter when it can't even analyze the categorical features. All right, so we're going to have to make some changes. But to do that, we've done some work. Let's document it. I want to show you what you're going to do for your checkpoint. In fact, here is your checkpoint at the end of this chapter. You're going to use the AWS data that you've been using before to keep things consistent and make it easy to continue working with the same data. But I want you to try out each of the techniques you learn in this chapter, filter-based feature selection, and you'll learn these next 2 in just a minute. And I want you to document what you do, because this is exactly what we do as part of the modeling phase. So here are 1, 2, 3, 4, 5 things I want you to document for filter-based feature selection. In addition, I would do one other thing. I would come back in here and visualize. I would actually copy these. You can copy it just like this. Copy these values, and you can make a chart out of this. Let me show you what I mean. Because one thing we didn't address, let's say, for a moment here, let's say that these were accurate, these zeros. Where do you decide, where do we make the cutoff? We said 6. And so it's going to take the first, now it's not going to take purchase by numeric, it's just showing us the dependent variable there. Its correlation is always 1. But it's going to keep 1, 2, 3, 4, 5, 6 variables, and it's going to cut off at gender and eliminate the rest of them. Well, how do you decide where to make the cutoff? You can see they're sorted from greatest to least, but what I would do is I would copy those values and put them here like I've done in Excel. So I just copied, pasted them right here, I highlighted this, and I just went to insert scatter plot. And no, not scatter plot, bar chart. And that's how I made this right here. So this is, in fact, I should put the title here, filter-based feature selection, Pearson correlation. Maybe we can make this smaller, filter-based feature selection. So we can see, all right, according to that technique, that scoring method, we can see visually where the chunks are, where the drop-offs are. Cars is in a class by itself, then children, marital status, and age, then it drops off significantly to income, homeowner, and gender, and then these are all zeros. If these were accurate, I would clearly eliminate those, but then the question is, which of these do I keep? The more of them I keep, the better my R-squared result's going to be, but the more of them I keep, the more likely I am to overfit my model. Now, these ones that are bigger here, these bigger effects, by keeping those, I'm less likely to overfit because those are such large effects that it's more likely that future data will, that these variables will continue to be significant. It's less likely that these smaller ones will continue to be significant. So what I would do is I would test a model keeping all 6 or 7, then another model keeping maybe just the top 4. And let's look at the differences in R-squared between them and see which one we want to keep. So that's what I've done. For the checkpoint, I would keep track of a chart like this for each of the weighted scoring methods that you try on one page. Then on another one here, and actually this charts page is optional. I'm not going to force you to do that, but for your checkpoint, I do want you to have one worksheet for each of the selection methods. So if you look back here at the checkpoint, it says have one for filter-based feature selection, try a variety of scoring methods and number of features to get the best R-squared. So here's the 5 things I want you to keep track of. I've got them listed along here. Feature scoring method, number of features, list of actual features selected, and then what's the R-squared and the RMSE you got for those models. So to get that, I come back here and I say, okay, if it's going to keep 6, then that means here, coming out of the filtered data set, I only see my dependent variable, purchase by numeric, and those top 6 variables, nothing else showing up. So I've listed those right here, 6 features. Now I just need to grab my R-squared and RMSE. I get those from down here on evaluate model. That's where I copied them from. My R-squared, RMSE scores, paste them in here. But I made a little note here. Pearson doesn't use categorical variables, I should say. So that tells me, all right, that's why I'm not using Pearson, but if I were to use it, here's what I get. And I've already run these 2 models. I'm not going to make you do them. So you can see that my number of features, I started with 6, went down to 4, but my R-squared dropped quite a bit. That's because I got rid of those 4 categorical variables. Even though my filter-based feature selection thought they were 0, before when I had 6 variables coming through, it still it still had a much bigger effect. But we're not going to worry about Pearson. Let's move on. What I want you to know is what the rest of these do. So as we switch from one to another, it resets my target column and my selected features back down to 1. So I have to reselect it each time. So if you're not sure which ones to use, let me go ahead and show you. Let's walk through each of them right now. You can even just test them out. Mutual information. Let's launch this. Let's pull over purchase bike numeric. I know off the top of my head one of them for sure that'll handle text-based data, which is Rsquared, but I think one other of them does too, and I can't remember which one it was. Let's try them out. So I'm just going to say desired features. Let's leave it at, let's start with 6 like we did before. Let's let this run all the way through and see what happens. Actually, no, let's just run this one first of all and see if it even gives us a value for the categorical variables. This should be really quick, so I'll leave it recording. Okay, let's take a look here. Features. All right, yep, commute distance, region, marital status, occupation, K. It is coming up with a coefficient for all of our categorical variables, like occupation, region, education, commute distance. So we'll note here that mutual information is one of the techniques, the scoring methods, that allows us to analyze categorical variables. You can always come back here to the documentation for a complete list of these, and it'll explain each of those scoring methods. Pearson correlation, we've covered that in class before, but then it describes how the rest of them work. And they're all just techniques for analyzing the relationship between two variables. So let's go ahead and finish this one out then, since we know we can use it. And what I'm going to do is simply document 2 or 3 models with different numbers of features. We'll start with 6 here, and then I'll probably go up and down depending on where this falls out. And we'll document our different options and which model we recommend. One thing I could have and should have done, I'm going to go ahead and copy these weights here, or these scores from mutual information, into my Excel file back here on my charts. I'm going to do another one. Let's do it like right here. Perfect. I'm going to get rid of those rows, delete age. These are off center a little bit. These go right here. Get rid of these things and that one. Then I'm going to do a copy, home, paste, transpose. There we go. Now we can delete these. Let's insert a chart over this. Insert bar chart. All right, beautiful. Let's call this one then. This is filter-based feature selection using mutual information. All right, so I look at this and wow, it's a really smooth drop-off. Clearly homeowner and gender numeric aren't doing anything. So let's have one model where we include 1, 2, 3, 4, 5, 6, 7, 8, 9. And then let's have another one where we cut off. We've already run 6, which will give us up through income. So let's report that one too. So let's start with 9 and 6, and let's report back on what we're getting from those. So we switch now to mutual information. We just ran a model with 6. Let's do another one with 9. So this is exactly what you're going to be doing for your checkpoint, by the way. Back here to our charts, that means we're keeping the first 1, 2, 3, 4, 5, 6. I keep switching to the wrong thing. There we go, 6. I'll just type it in here. Age, cars, commute, children, education, income. Okay, so I can clear all up from that. Then with the 9, that means I'm also going to be including region, marital, occupation. Region, marital, occupation. All right, cool. Expand that, it's not too important. So let's grab our Rsquared and RMSE from this model. This is the, again, it's my 6 model with mutual information. Visualize. Whoops. There we go. Rsquared, RMSE. All right, so this one, the reduced, well, the model of 6 isn't as good. So, hold on, I'll come back to that topic in 1 second. Let's run our model of 9 and grab that one. Okay. While that one's running, I want to talk about what we're seeing here. So here's what's interesting. When Pearson versus mutual information is used to determine which variables to include, it's not changing the actual importance of those variables in the multiple linear regression. Cars here has just the same effect as cars here. But this combination of variables, according to the mutual information, was actually not as good of a combination as these 6 variables as determined by Pearson correlation. Does that mean Pearson's better? No, not really. It just means that the 6 variables it chose based on this scoring method happen to actually do better in an MLR than these 6 variables based on this scoring method. So even though this scoring method accounted for the categorical variables, it was actually a worse representation of which was actually most important. But that is all assuming that multiple linear regression is the best model. So we don't make a lot of assumptions yet. We're still just going through very methodically and analyzing all of our different possibilities. So anyway, let's see what we get with 9. This should be something that's much better, I imagine. Yep, 10.42. Let's grab RMSE. So in other words, based on what I was saying before, let's say that mutual information and Pearson correlation both agreed with the same 6 variables. Let's say that they both said that this 6 were the ones that we should use. The Rsquared and RMSE would then be the same for both of them because they're both still getting analyzed in an MLR model. Anyway, I'd say that's good. Let's go and try one more. Now, because we're including categorical variables, I'll just share with you right now, the only other one that's going to be useful is going to be chi-squared. So mutual information and chi-squared are the only 2 that will handle categorical data. If you're not using categorical data, though, you should go through and try each of them and run a couple models or maybe even a few models with each. But this helps us out a bit. Let's go with 6 again. And let's see where this gets us, and we'll make a chart one more time. Let's run selected. Okay. Features. All right, I'm going to go ahead and copy these and go back and add them to my charts. Let's paste. I'm going to, somehow it gets these off each time, adjust that. Let's copy that. Paste transpose, copy this, paste transpose, and then let's clear everything from those cells. All right, now let's come up with a new, let's insert another bar chart. Okay, this is filter-based feature selection. Chi-squared score. So again, just like Pearson correlation and the others, it's just a measure of the relationship between 2 variables. So this is age with purchase bike numeric, cars with purchase bike numeric, commute distance with purchase bike numeric. So this says that age seems to have the best one. If we look back at our charts, age is number 1 in these 2, and all the way down to number 4 in this one. Cars is number 1 there, number 2, number 2. So cars seems to be a little bit more consistently up in the top than age. Anyway, so let's take a look at this. It looks like clearly we should get rid of homeowner and gender based on this. Let's do one model with 1, 2, 3, 4, 5, 6, 7, 8, 9. We'll do a 9 variable model. Again, we're looking for a natural cutoff, and this is so smooth, there's not really a natural cutoff anywhere where all of a sudden you see a bunch of other variables that are really far down. So I'd say let's do a 9 model, and let's just do a 6 again right here, just to arbitrarily give it another spot to cut off at. But it actually looks like, are these identical? Age, cars, commute distance, children, education, income, region, marital status, occupation, homeowner. Yeah, chi-squared mutual information gave us the exact same rank order. So what does that mean? I don't even have to run all the way through evaluate model. I can just come over here, because I know if the chi-square, I know if the order is exactly the same, then a 6 and a 9 is going to come up exactly the same as it did right here with this one. Let me prove it to you real quick. So filter-based feature selection 6, let's run that. Get that going all the way through. So, yep, let's let this finish real fast. Okay, right click, visualize. 0.073932, 0.0739 right there. Same thing. So again, these are scoring methods that tell us what rank order, what should we put these variables in terms of importance. It doesn't actually do the prediction. The prediction still happens back here in the trained model by using linear regression. That's why it's still the same if I use the same variables coming through. Anyway, that wraps up for filter-based feature selection. This is what you need to record for your checkpoint, but with the AWS data, or if I've changed the data set, whatever data you're asked to use for your class, that's what you need to use. But here's what I'm looking for in the checkpoint. Next, we're going to create another sheet for permutation feature importance and PCA, but I'll stop this video for now.